InRealStream is showing a black window. Like, yes, it has come. Okay. In InRealStream, it has come in InRealStream format. Like on the sideway, we three are there. Very nice, automatic. See, in Zoho, we are at the top. In InRealStream, we are at the right side, right panel. Okay. So here, let me put your. I mean, first I will start with the what is that? Uh, the flyer image. Yes. Let me add the flyer image. What is there? It is there. I can do it, or they don't allow me. Just a minute. TMP. Maybe it is already doing. Just a minute. Let me see in LinkedIn. Oh, we are live. We are live on LinkedIn. Yes. Yes, it is going. Yes. Okay. Okay. Hey there. This is Debesh, the info security researcher. Welcome to my LearningTimes podcast. We are continuing with the second part of the online workshop, mini workshop on computational photonics. Today, it will be the second part. The first part we streamed on December 6th. It was computational photonics and introduction. Today is the second part, and the part 2 title is Finite Difference Methodologies and Real World Problem Solving. The guest speakers are Professor James Cole and Dr. Saswatee Banerjee from photonicwavesolution LLC. So, without much ado, I will hand over the platform to Professor James Cole and Dr. Saswatee Banerjee. Please, the platform is yours. Please start.
Good evening, everyone. We're going to have this podcast in two parts. So one part I will present, and the other part will be presented by Dr. Banerjee. So I am James Cole, and I'm going to discuss the non-standard finite difference time domain methodology to solve Maxwell's equations. Perhaps you have heard of the finite difference time domain methodology, and it's a very popular method, very useful method in solving practical problems. What we have done, what I myself and Dr. Banerjee have developed, is a new methodology called the non-standard methodology. The non-standard methodology is very similar to the normal finite difference time domain method that you will see in engineering textbooks, but it's much more accurate. And the way we achieve this accuracy is what I'm going to discuss this evening. All right, so first of all, I need to, let's see, I need to go here. Oh, it's something wrong here. I can't progress. How do I? Okay, got it. All right, so first of all, let me discuss qualitatively the difference between a standard and a non-standard model of a differential equation. As you know, the wave equation and Maxwell's equations are differential equations. In very few cases can you actually solve these equations for practical problems, so you need to have a numerical methodology. And there are many different numerical methodologies, but one important methodology is the finite difference time domain method. But I want to just discuss first in general, what is the difference between a standard model and a non-standard model? In very easy terms, it's you take the differential equation and you make a model of it using finite differences. And this is analogous to a literal translation of one language to another. We could take English and then look in a dictionary and find word by word translate to Hindi. But this would most of the time fail to capture the true meaning of the English sentence. The Hindi might be almost meaningless. And in the same way, if we take a differential equation and then put the same parameters of the differential equation into the finite difference model, it usually will not be very accurate. So in a non-standard model, we adjust the parameters of the differential equation based on a priori information about the solution. And what do I mean by a priori information? I mean some advanced information that we have. For example, if we're solving Maxwell's equations, we're usually interested in waves, electromagnetic waves, light waves, for example. And so we know that the solution is a wave. We don't know the amplitude of the wave. Maybe we don't know the frequency of the wave, but we know it's a wave. So what we can do is we can adjust the parameters of the differential equation using this a priori information. And we can adjust them such that the finite difference model is a very good solution. That is, it will closely match the solution of the differential equation. So we want the solution of the difference equation to be the same or almost the same as the solution of the difference equation. All right, so before I go into the method, I want to introduce some of the basic ideas of finite differences. And I'm sure everyone has studied this method in elementary calculus, how to approximate a derivative. So this is called the forward approximation. That is, if we have a function, we want the derivative, f of x plus h minus f of x, and then divided by h. And the error is proportional to h. Well, there's some higher order terms, but the leading error term, the largest error, is proportional to h over 2. Similarly, we can have the backward approximation, and there the error is also proportional to h over 2. Finally, there is the central finite difference approximation, the point where we want to know the derivative. We go one half step forward, one half step backward. That's why it's called central. And here the error is proportional to h squared. Now, in general, the central finite difference approximation is the most accurate. But if these derivatives, this third order derivative, happens to be very large, it may not be the best one after all. But for the purposes of solving Maxwell's equations, the central finite difference approximation is the one we're going to use. Now I want to introduce some notation. This will make the presentation much easier to view and understand. So this is a difference operator with respect to x. So I'm introducing central difference operators. So one step forward, one step backwards, the difference. The second difference, it's the difference of the first difference. And so now it's one full step forward, one full step backwards, and then minus this. Okay, so we can say that the first derivative is this d sub x divided by h acting on f of x, this operator. The second derivative is this second order difference operator divided by h squared acting on f of x. So we can make this notation that the second partial derivative with respect to x is this second difference with respect to x divided by delta x squared. second derivative with respect to t, second partial derivative, is divided by t squared. Okay, so let's start out with the one-dimensional wave equation. We can extend this to Maxwell's equations in 2 and 3 dimensions, but let's start out with a very simple example. So here is the wave equation. So this is the partial derivative so this is the wave field. If you think of a string, this is the height of the wave. If you're thinking of light, this is the amplitude of the light wave. So the second partial derivative with respect to t, this is the velocity of the light. If you're in a medium, this may be less than the velocity of light. And then the second partial derivative with respect to x. So we make a finite difference model by substituting these finite difference approximations for the derivatives, and this is what we get. So this is our finite difference model of the wave equation. Now, what we can do is, using this fact that this is the definition of the second difference operator, which I showed you before, and so we have this dt squared acting on psi, and now we solve for psi of x t plus delta t, and this is the textbook algorithm of fdtd that you will find in textbooks. So this is it. Now, there's an old saying that the devils are in the details. And so there are some things that you have to know. I'm not going to, I don't have a lot of time, so I won't discuss this completely. But you can't just have any value of delta t squared or any value of delta x squared. They are constrained. In the case of one dimension, you must have v squared delta t squared divided by delta x squared less than or equal to 1. And then, since we are interested in waves, the wavelength, you need at least more than 2 grid points to represent the wave in space, and you need more than 2 time steps to represent the wave in time. That is the period of the wave. This is the wave period. So you need more than 2 time steps to represent the wave period in time. Now, there's another complication. When you calculate anything, you're on a finite domain, a finite computational domain. You don't go infinitely into space. You don't go infinitely forwards and backwards into time. So you have to define these quantities on the computational boundary. Again, that's a complicated issue. I won't discuss it right now, but it can be done. So you can simulate an infinite space-time in this algorithm. And then finally, one more item. You need 2 wave fields to start the iteration. You need an initial time step at time 0, and then 1 time step. We can get around this by using a source, but I'm not going to discuss that right now, because maybe we don't know these fields in general, but we can avoid knowing them. But again, that's another devil in the details that I won't discuss. But later on, I can discuss this if anyone is interested. All right, so now let's look at the standard FDTD algorithm and the errors. I told you that it's not very accurate unless you make delta x and delta t very small. But if you make delta x and delta t very small, you need a lot of computing power. You need a lot of resource. You need a lot of memory. So we'd like to reduce the time needed to compute and the memory needed to do the computation. And to do that, we can make the error of this algorithm very small. And in fact, in one dimension, we can make the error to be 0. In 2 and 3 dimensions, we cannot, but in 1 dimension, we can. And I'm going to show you exactly how we do this. And I add that we can make the error 0 in 1 dimension, and we can make it very small in 2 and 3 dimensions. So here is a solution of the wave equation. Now there's an amplitude out here. And now let's put this. So here, if we put this solution into the wave equation, we get 0. If we put it into the finite difference model, it's not 0. That means there's an error. And the failure, the amount by which it does not vanish, is the error. So here is the model error. I can make it vanish. If we change this v delta t squared over delta x squared and replace it by v tilde squared, which is this quantity, and if you look at this carefully, if you think about it, you will realize that by changing this quantity into this, you can make the error vanish. And this is a non-standard model. That is, this is equivalent to a word-for-word translation of one language into another, a translation of the wave equation into a wave equation model. This is another better translation, just if you think of it that way. Okay, now let's look at the standard model and the non-standard model. So the standard model is this. The non-standard model looks exactly the same, except that the parameter is different. That's all. So the conventional textbook FDTD is this one. The non-standard FDTD is this one. They look exactly the same, except that this part is replaced by this part. So the standard error is large. The non-standard error is 0. And furthermore, for all frequencies, omega, that is the angular frequency, and wave number, which satisfy this relationship, the error vanishes. All right, now I'm not going to get into this here, and I won't derive it, but if you have a source, that you produce the light with a source in your calculation, you need to adjust the amplitude and the index of refraction. So we have a practical case where we have a wave equation with a certain index of refraction, and we will change the source amplitude to something different from the physical source, and we will change the index of refraction to something different from the physical index of refraction. Again, I won't derive this, but I can show you further details later on, or we have references about this. Okay, so again, I'm just going through some of this. This is the analytic solution. We put the analytic solution into this model, and then we can show that the error is indeed 0. We can extend this to 2 and 3 dimensions. And let me just jump a little bit ahead. In 2 dimensions, we need a derivative with respect to x, a partial derivative with respect to x, and a partial derivative with respect to y. What we can do is we can replace these partial derivatives. It would look like this if you visualize it: left, right, up, down, partial derivative with respect to y, partial derivative with respect to x. That is, we use points on in the space-time grid to compute these partial derivatives, just as we use points in the space-time to compute the partial derivatives in 1 dimension. And we use some diagonal information, and we combine them in a clever way. So again, I'm not going to go into those details, but suffice it to say, we use all in 2D, we use all the grid points on a square around this. This is where we want to compute the derivative, the Laplacian, I should say. And we use the information on the diagonals. We're using more information and getting a better approximation. And we combine them in a certain way, and like this. And this is the 3-dimensional form of this. And if the operator for z is 0, then we reduce to the two-dimensional form. Okay, so here is the Laplacian of the error of the Laplacian for the standard finite difference model. It's kh squared. K is, remember, the wave number, divided by 16. Here it is kh to the 6th divided by 256. So this is a very small error. And so in 2 and 3 dimensions, we have a nearly exact representation of the wave equation. All right. So we can. So now again, the wave equation. This is the wave equation model, and in the non-standard method, we have the parameters a little bit different. The index of refraction is represented differently, and the Laplacian is by this tilde represented differently. Now I'd like to go back to what I said up here, where, remember, I said that in this wave equation model, in this fdtd, there are devils in the details, and one of them is numerical stability. Anytime you solve something iteratively, and there are many kinds of iterations, you always have to worry about something called numerical stability. And what this means is that mathematically, you may have a very accurate solution. You may have an exact solution to something, but when you try to compute it, the computational result may be very different because of round-off errors in the computer. So, for example, if you try to represent 1/3 in the computer, or 1/3 as a decimal, you know that 1/3 is an infinite decimal, and you can only represent it with so many bits, and then you have some truncation error. So for the same reason, you will have errors, and you have to worry about this ratio. Let's go back to here. You have to worry about this ratio, and if it's smaller than 1 in 1 dimension, then the truncation error and round-off error will not accumulate. They will not grow exponentially, and you can have a good calculation. Otherwise, they can grow exponentially, and I will show you an example of this very soon. So here are the speed limits. So in FDTD, there is an algorithmic speed of light, and there is a speed limit. So in 1 dimension, the speed limit is 1. The speed of light in your algorithm is 1. This means that the light can travel 1 space step in 1 time step. However, in 2 dimensions, the light can only travel in the practical calculation. Theoretically, it can travel 0.7 space steps in 1 time step, but in the practical calculation, only 0.67. So the speed limit is lower. And in 3 dimensions, the speed limit is yet lower. Again, the theoretical speed limit, the practical speed limit. So if this is a philosophical point, if the physical speed of light is determined by some sort of nature, by FDTD and nature, then it would depend on the dimensionality and the geometry of space-time. What do I mean by the geometry? I mean, are the space-time points connected like this or like this? All right. And let's look at a 1-dimensional example. So this is the current value of the wave field, of 1 point in the wave field. And to compute the next point, we need information from the left and information from the right and information from the previous time step. This is all combined together to give the new wave field at each point. Now, information can only flow the maximum speed is 1 space step. the information can go one space step in one time step. Now, if in my algorithm I set the algorithmic speed below the speed limit, some information will still travel at the speed limit. And I'd like to show you an example here. So I'm going to look at a one-dimensional wave. Let's start it. So here's a source right here, and it is right in the center, and it's generating a wave. Now, this black line is the main signal. That is this is this light going at the speed of light that I set below the speed limit, so less than 1. But some light, a very small signal, this is greatly magnified. This is perhaps 1 billion times more than that, maybe 10 to the minus 15 less than the real signal. So this is not a true scale. So this is the real speed of light. This is going at the real speed of light, the black line. And this is the main signal. This is what is called the precursor signal. And it's very small compared to the main signal. And it's traveling as if the speed were 1. Here, the speed has been set to less than 1. I set it to 1/2. And it's going at this lower speed. Now, there is a real precursor. There's a very famous textbook by Jackson called Electromagnetism or something like that. And you could take a laser and shine it through a block of glass. Now, in the glass, the speed of light might be 1/2 the speed of light, the vacuum speed. And most of the signal will go through the glass block and will be detected as if it were traveling with 1/2 the speed of light. But a very small portion of the signal, very, very small portion of the signal, will arrive as if it had traveled with the speed of light. The physical effect is actually dispersion. But it's very interesting that the dispersion on the grid, the algorithmic dispersion, produces this precursor wave. So again, this is the same thing. I've showed this. Here, the algorithmic speed of light, I set it to 1/2, but a small signal propagates as if the speed were 1, and that is these blue dots. And the black is the regular signal that travels at 1/2 the speed limit. Okay, now I'd like to just discuss the difference between standard and non-standard FDTD and the accuracy. So what I have here is there's something called Mie scattering, MIE. This is named after a person, and this theory was published in the early 20th century. And there is an infinite plane wave of light coming in on an infinite cylindrical dielectric. This is the cylindrical dielectric is white. The infinite plane wave comes in and scatters off the cylinder. We only show here not the incident field, but the scattered field. So this is Mie theory to calculate the scattered theory, and I'll show you the Mie theory in a few minutes. And so we calculate this with the non-standard FDTD and with the standard FDTD. And we're using a very coarse grid, only 8 grid points per wavelength. This L, the Greek letter didn't come out on this computer, unfortunately. I just noticed it. Anyway, this is the wavelength. So the grid spacing is 1/8 of the wavelength, and the cylinder radius is 3/4 of a wavelength. All right, so I'm going to show you, first of all, the standard FDTD algorithm. So this is I'm not running it live, but I am running it. Here, I have to click it here. All right. So the infinite plane wave is coming in, and we're looking at the computed intensity and the computed field. And this is the scattered intensity on a contour around the the cylinder. So what you're seeing here, this is the intensity on a contour around the cylinder. Oh, this is the non-standard method. This is the non-standard method. And you can see that it's very, very accurate. It's almost exact. So the me theory and the computed intensity are quite good. Okay. Now, we don't need to watch this till the end, but you can. So here is the scattered field in the standard finite difference method. So let's look at this one. The standard finite difference method, as you can see, it gives you a very bad result. It misses the computed intensity, misses this central beam, just completely. And again, the black line is me theory. The blue line is the computed scattered intensity around the contour. So again, it's not very good. Now, I'd like to just show you why we need FDTD, or why we need any numerical solution. So here is an analytic solution of me scattering off of a cylinder. So an infinite plane wave comes into the cylinder and produces a scattered wave field. And the scattered wave field is given in terms of Bessel functions and Hankel functions. And it's an infinite sum of Bessel functions and Hankel functions. And so it's quite a difficult thing to calculate. Even if you have the analytic solution, you have to sum all these Bessel functions and Hankel functions. Now, if you had a square cylinder, there is no analytical solution. Why not? Here, you have to match the derivative on the boundary, inside and outside, must be the same. And the wave field must be continuous across the boundary. That is the derivative, the normal derivative, and the wave field must be continuous. Now, there's no solution. You absolutely must have some kind of numerical method. All right, now, this is some of the work that my colleague, Dr. Banerjee, has done, and I'm not going to discuss this. I think she will give you a good presentation about it, but we use the FDTD method, and she has extended this when there is dispersion in the metals. And she also did a lot of work analyzing some biological systems, which I think she will discuss later, and making models of biological systems using non-standard FDTD. We've used this to develop a device that can separate wavelengths for multiplexed communication. And this is a patent that we filed in Japan. So next time, one of the topics that we will discuss is nonlinear optics, and there are other topics that we can discuss according to what you would like to hear about. And our work is described in detail in this book. And if you do a search for non-standard FDTD, you will see that there are many papers, both our papers and other people have written papers. So later we will have some questions. And I just want to anticipate one question. You may ask, why do we use non-standard FDTD and not a higher order finite difference method? It diverges. It will be mathematically more accurate, but a fourth order method will fail. A non-standard second order will give you a very accurate solution. So with that, I will turn over the forum to Dr. Banerjee.
If there is any question.
All right. So first of all, are there any questions I can ask? We can have a few minutes for questions. You can put it in the chat or ask me directly.
Okay. Please raise your hands. I can see 3%. You also can see Atin Mukherjee, Konik Palodhi, and Rahul Haldar. Please raise your hands so that we can put you on microphone or video, and then yes, please, Konik or Rahul Ratin, please press that hand button so that we can tell you. Okay, Konik will ask something. Okay.
Can you see?
Konik will, Konik, your microphone is mute.
Oh, I cannot see. Oh,
It's okay. You answered.
Konik,
yes.
your microphone is mute. Please come here and you can talk with video or audio, whatever you like.
There.
He'll
Yeah.
come. Probably he's attaching. I mean, there are some things they have to click. Maybe they have not done. It will take a few seconds.
All right.
Yes. Konik is has raised the hands. Konik will ask the question very soon.
He is unable to use the mic. So
No. Konik, has they written that?
yes. Can you see the chat, please?
Okay. I am unable to use the mic. I'm going to type. Okay, type it. Okay, please type it.
All right. Is it coming?
He will type the question in the chat. Open the chat.
It should come out here.
Yeah, maybe it takes a couple of minutes.
This is.
All right.
He will type. He has written. The question is, you open your chat, Saswatee or James. You can see.
Yes, we can see.
All right. Yes. All right. So I can answer your question. Let me just read the question and then I will answer it. The question is, if non-standard method has an anisotropic nature of the solution, how can it be more accurate than higher order solutions? The non-standard method is not anisotropic. So if you put a source in the middle of the say a two-dimensional wave field or a three-dimensional wave field, then you will see that it is not exactly isotropic, but it's much more isotropic than the standard method. And in fact, it is this higher isotropy. Let me just show you what will happen, why it is more isotropic. Right here, if you put, this is the standard method in 2 dimensions. So waves will come out in a square pattern. Gradually, they will turn into a little bit more circular, but they will not be isotropic. The wave speed this way will be different from the wave speed to the left and the right. So the diagonal wave speed is different from the from the left-right wave speed. Here, we've adjusted. This is where the superposition comes through. This superposition here is what makes this more isotropic. We're using these diagonal points. So we've adjusted the superposition parameters such that the diagonal wave speed is the same as the left-right wave speed. And this makes it much more isotropic, and then it makes it much more accurate. And so the reason why, right here, the reason why the non-standard method has this large error is that the scattered wave field is less isotropic. I mean, a point source, if we put a point source here, it would be less isotropic. than the non-standard method. So that is exactly what makes it more accurate than higher order solutions. And again, let me emphasize that a higher order solution really doesn't work very well. Here's a standard second order finite difference time domain algorithm for the harmonic oscillator. Okay, now here is a fourth order finite difference time domain algorithm. Mathematically, on paper, it's much more accurate. But here, look at this. This blue line, this is the fourth order. For a short time, it follows, the black line is the exact analytical solution of the harmonic oscillator. This is time, and this is the oscillator position. So for a short period of time, yes, it's very good. And then after just a few time steps, it dramatically diverges. And we can make an exact second order finite difference time domain algorithm for the harmonic oscillator. I'm not showing it here, but we can make this an exact second. Maybe I have this here. This is the fourth. I don't have the, okay, I didn't show, yes, I do have it here. So these red squares are the non-standard, no, they're not the non-standard, sorry. Anyway, the circular ones, I think, yes. And I think I showed both of them, but maybe not in here. I cut some slides out. Anyway, the point is, if you try to solve the wave equation or Maxwell's equations with higher order finite differences, it won't work. It will be numerically unstable. And I can give you a reference that proves this. There's a book by Ronald Mickens, Mickens, and he has proved that higher order finite differences, that if you use a fourth order finite difference to solve a second order differential equation, it will fail. And this is a dramatic demonstration of it right here.
Okay, Koenig, do you have any other question? Excellent, sir. He's writing one more question. Oh, another more question. Please read. James. One more question from the same person.
All right. You've
please read the question. Please read the question.
All right. So let me just read the question so that everyone else can understand. So one more question is whether this is dependent on the sampling period being regular and whether adaptive irregular sampling can be used for generating the solution. You are talking about an adaptive grid and maybe an irregular grid. And my experience, there are people that claim to use irregular grids in doing finite difference time domain methods. And maybe they work in some special problems. So for example, if you have very large structures, very smooth structures, and then very small structures, you might like to use a small grid in one place and a large grid in another place. And some of my colleagues have tried this, and to some extent it works. They have succeeded in doing making it better than before. I myself haven't done too much of this, but let me address the question about sampling. Again, this comes down, let me go back to a previous slide here. There is something called Nyquist sampling. So if you think of a sine wave on a grid, think of just you made a graph of a sine wave. All right, current slide. From the current slide. All right, imagine you made a graph of a sine wave. Now at the first grid point, when you start, the sine is 0. Then in the middle, the sine is 0. And finally, at the end is 0. So if you used two intervals, 2 grid intervals. I should have a picture of this. I don't have it immediately available. Wait, maybe I do. Wait just a minute. I do. Right here. Just one moment. Let me get you a picture. Right here. All right, look, here is a sine wave. Right here. This black line is a sine wave. Here, let's start from here. This is a sine wave, okay? Now, if we looked at this grid point, and this grid point, so that would be 2 grid intervals. If we had 2 grid intervals, the wave would be 0. So we must use more time steps. This is a time. So if we had our spacing, our sampling so large that we only see 3 points of the sine wave, we wouldn't see anything. We would just see 0. So we must have, so the Nyquist for 2 dimensions, right here. Let's go here, go back here, right here. Yes, the Nyquist sampling criteria says that the time step, the ratio of the period of the wave to the time step must be greater than 2. And similarly, if you're sampling on space, the ratio of the wavelength to the space step must be greater than 2. And in 2 and 3 dimensions, let's just go here. Your distance on the grid is, if this is 1, 1, then this is square root of 2 over 2. So the thing is that, I mean, this is square root of 2, not square root of 2 over 2, square root of 2. So the point is your sampling, your space step will have to be bigger. So the higher the dimension, the bigger the space step must be. And this comes down to the Nyquist sampling. So there is a minimum amount of sampling that you can do. And that will also determines not only the accuracy of the algorithm, but also the stability of it. So thank you. That's a very good question.
Okay. Can you hear me?
Yes, I can hear you.
Yeah, there is a question in LinkedIn, one comment. Shall I copy and paste it here? Because you cannot see it here.
Mm-hmm. Yeah, if you can do that.
Yes, I'll just paste it.
Yes, I can read it. Yes.
Shamsuddin posted. Yes.
Yes. So yes, I also thank the Optical Society for appointing me as editor, and I've been very busy lately. I will be carrying out some of my editorial duties now that we are in the holiday season. So, this is it's a great honor to be part of the Optical Society of India, and I will publish some of my papers also with the Optical Society of India in the future. So yes, I'm glad to hear your comments.
One comment from LinkedIn I pasted. One Shamsuddin Ismail Dansmall wrote. So how
Where
can
do I
you?
see it?
So it is in the question answer Q&A.
Okay.
I have copied and pasted
Right.
from DC.
So
you can see.
So the
Just
real
read it.
overflow waves, how can you understand the real overflow wave speed? I mean, the real wave speed. Okay. So in the algorithm, let me just show you. In the algorithm, let's look at the algorithm here. Let's just look at the one-dimensional case, okay? So in the algorithm, we have delta t and delta x. So let's suppose that we make the time step to be 1. Then we have to have this. So we can define the time step to be 1 and the space step to be 1 in the algorithm. And then v squared is less than or equal to 1. Okay. Now, how do we translate to the physical wave speed? Well, we would say that delta t is 1 in the algorithm, but it's so many nanometers in physical space. So our units, let's suppose that the physical wavelength is 800 nanometers. Okay, so now I would take the space step to be 100 nanometers. So I would say delta t is 100 nanometers, but I don't put that in the algorithm. In the algorithm, I'm using a unit of measure where one grid unit is 100 nanometers. And but that one grid unit corresponds to a physical distance of 100 nanometers. Similarly, the time step would be such that I can't remember exactly how many picoseconds or it would be, but the time step, let us suppose that I say, okay, the wave period is, let us say, 1,000 picoseconds, and then I discretize that the delta t is 100 picoseconds. So now my time unit in the algorithm is 100 picoseconds, but in the algorithm, I say that delta t is one time unit, one algorithmic time unit. And so in this way, I translate back to physical space and physical time. And similarly, I can always say that the amplitude of the wave is 1, but my grid amplitude can correspond to so many volts, or the electric field is volts per meter. So I would say that the grid unit is might be let us say 10 picovolts per millimeter or something like that, and so I can easily translate back and forth to the physical unit. And I can give you, well, I don't have time now, but I can give you an example of where we do a calculation and actually get the physical unit. So it's very easy. Once you have your results, you can very easily scale them to the physical units, to SI units or whatever units you might prefer.
Okay, thank you, Shamsuddin Ismail on LinkedIn. You might have got your answer. So you can proceed with the next part of the today's part 2 workshop.
Okay, so I'm turning over the forum to Dr. Banerjee.
Yes. Just a minute. Another hand is there? No. Okay. Okay, start.
So we have changed places now in this scene. Okay. Oh, the microphone, have you muted here? Oh, yes, it's muted. Okay. To get your image there. Hold on, your image is here. I'll get out of the way so your image appears. It's okay.
Okay, this looks like something. Okay, hello and welcome everybody to our podcast. So my name is Saswatee, and I work in this field, this applying computational techniques in photonics for real world problem solving. So I'm an applied scientist, applied physicist by training. So I did my PhD from my first PhD in applied physics with optics and optoelectronics specialization from the Department of Applied Physics, Calcutta University, from Professor Ellen Hasra's group. And that's where I met Dr. Choudhury, and he was our senior. And this year we again reconnected. And so I thought this is a good idea that we start something, a little podcast, and talk about things that we care about. So without much ado, let's start into the topic. So as you saw from Professor Cole's discussion, that there are these finite difference methodologies he talked about that. And my duty here is to talk about the real world problem solving that I saw in my career. And I learned something a little bit. I see things slightly differently. So I will try to explain that to you, at least a little flavor of that. So some of the thing is what I noticed is you do need this nanophotonics, and you do, I mean, there is a tendency to use nanophotonics in optical devices. So I did dealt with some optical devices that uses nanophotonics for this unconventional functionality or even conventional functionality. So now here, when you are talking about this photonic design simulation, I am actually more talking about the visible domain. I worked in visible domain and near IR basically. So in those domains, I mean, you do need this modeling, basically computer-aided modeling, because the structure becomes very small, really small. Say we are talking about wavelength scale structures, that is few hundred nanometers or micrometers. And then what you will see is a diffraction patterns or diffractive characteristics, which are polarization dependent. That's where you really need to do some rigorous solution. I mean, rigorous results you need to see. So that's where. And then the problem is, because these are really small features, so when you are going into fabrication, I mean, this is my personal experience, that the fabrication teams, they always will have some issues, because it is pretty difficult to realize exact designs. So there will be some, you have to go on feedbacking into the fabrication side, and fabrication side will come back, and you have to do your modeling simulations, and you have to go on, give them some better directions basically. So this is where it is very important to do this kind of simulations, this kind of modeling. So here, as Professor Cole already explained, so we are a little bit discussing about the Maxwell's equation solvers. So let's go to the next slide. From this real world problem solving, what do I mean by that? One thing is, I mean, basically what we are trying to see here is light interaction with media and structure. These two things in photonics, basically, you will care about the material medium and you will care about the structuring, basically. So there is this light propagation through homogeneous media. Now, you saw Professor Cole was talking about the wave equation. Now, wave equation is something that you can use for example, when light is propagating through the homogeneous medium. Now, then with this nanophotonics, what you can do, you can design artificial media. That is, you can have nanoscale or microscale modulating the media, basically. So that gives rise to artificial media. So you can do this light propagation in artificial media, and then the characteristics will be different. So we can talk about it. There's a lot of things there. And then there is this light propagation across interfaces. This is very important, because anybody who deals with electromagnetism, you will know that whenever light is coming between the two interface between the two media, there are these electromagnetic boundary conditions that actually dictate how they really either getting reflected or transmitted or absorbed at the boundary between the physical boundary between the two media. So we'll see a little bit of that. And then there are a couple of other things. For example, light emission. This is an interesting phenomenon. So of course, you can think about, I mean, lasers and LEDs. And LEDs are, as you know, is more spontaneous emission device, or fluorescence you are seeing there. And photoluminescence is another thing. It's very commonly used for characterization techniques. And then there is another thing that happens, that is light absorption. This is just the reverse of what you are seeing in light emittive devices. That is, here light is coming and this is absorbed in the photodetectors or photodiodes, basically. So as I already said, that I'm more interested in the visible domain. I work in the visible domain a lot. So what I see here is actually, in reality though, we don't really measure the real-time interaction so much. But then, so we actually, in optics, we measure more like the steady state behavior. I think Professor Cole did show you that the precursor wave, etc. There are these transient behaviors which actually come out if you study it in real time. However, in most of the optics measurements, we actually don't measure that. We actually deal with steady state phenomena. Now, so when you deal with steady state phenomena, actually you don't need to do finite difference time domain. You don't need real time, wave propagation. What you really care, you can actually solve it in frequency domain. You would argue that, okay, let's solve it in frequency domain and let's see the final result. As an argument, that's actually true, but in industry, actually finite difference time domain became a standard way of solving these problems. The reason is, it's not just that you care about the real-time behavior, which is good if you are looking at it, but it's also because the algorithm itself is easy to implement, and it's a robust algorithm, and it can be stable with a lot of little details. There are a lot of little details, but it can still be more stable and easier than, for example, the finite element methods. So that's one reason why it is so, became very important basically in this domain. So if I go to this is a little example as I was talking about the interfaces, etc. So this is an interface between, you can see on the left-hand side, this is an interface between a high index medium and a low index medium. So, and what is happening here, that the incident beam is hitting, the light is coming from the from inside the high index medium, and it is hitting the interface. And you can see, because it is coming at an angle which is more than the critical angle here, so the light is totally reflected and reflected back into the medium. So this is what is, of course, we do know about total internal reflection, but then this is guided by these electromagnetic boundary conditions. The reason these boundary conditions are important, here I did it with FDTD. It's kind of hidden. You are not really seeing the electromagnetic boundary conditions, because this is a good point about FDTD, because it is automatically, once you set the initial condition, it is automatically implemented, basically. So you are not really seeing this, but you need to know that there are these electromagnetic boundary conditions, because when you are talking about the frequency domain, if you are trying to solve this problem in frequency domain, then you really need to consider these electromagnetic boundary conditions. So then I would say, then just consider the right-hand side picture. You have a nanostructuring of the surface, and you can see that immediately this light is coming out, basically. So that's the effect of nanostructuring, and it is being used in many actual real devices, basically. So this little demo I did actually for light extraction for LEDs, in fact, because there the problem is light is emitted in a high index medium, high index semiconductor, and then the challenge is to extract the light into air mode, basically. So that's where I saw. However, this is just in 2D, and this problem will be much more complex, and you can do many things when you go to 2D and 3D. But this is just a simple demonstration. Now here I will little bit go into, I think Professor Cole showed you the wave equation, basically, and how you solve the wave equation. Now I will little bit talk about the Maxwell's equations. Not really, I won't go into the Maxwell's equations, but what I'm trying to show you here is the propagation or the interaction of material is in fact all guided by the Maxwell's equations. And the reason we care about the Maxwell's equations, as I said, that the polarization-based diffractive property. So what is polarization-based diffractive properties? Meaning you have this different, in a full 3D form, you have this electric fields Ex, Ey, Ez, and equally, magnetic fields Hx, Hy, Hz, basically. So if you write the differential form of Maxwell's equations, it will look like this, the D and H, you can see this. And I guess you all know that this D is actually the displacement vector. And this thing that I want to focus on is that this D has something called the material property, which is permittivity, which is known as permittivity, electrical permittivity, this epsilon. Another little thing that I would say that in optics, actually, we don't really see it in this way so much because we don't really study the real-time propagation so much. So we see it in frequency domain. If you write it in frequency domain, actually in many cases for many materials, you can take this epsilon out of this equation and you can put it in front of it. But when you are writing in time domain, and what will happen is actually this is not so simple. It is actually a inverse Fourier transform relationship there. Why that matters, that's some amount of discussion. But before going into that, let me tell you that this epsilon is one single parameter that is important in determining the behavior, the interaction between light and material in most cases, most of the cases that we deal with in optics and photonics. Most of the cases, this magnetic permeability is taken to be 1, so no issue. But there is also this parameter, this electrical conductivity, especially when you are dealing with semiconductors, metals, and dielectrics. For dielectrics, okay, conductivity is 0. But for semiconductors and metals, etc., there is this electrical conductivity. Now, when we look at this electrical permittivity, so this is basically a complex quantity, right? And here on the right-hand side, I show you something called Lorentz model. And this is an analytical model, basically. Now, let me tell you that this is the reason I like this thing, because it is a simple way of looking at it, but it still brings out the physics, basically, how this parameter behaves. You can see this. However, it is not something that you are seeing in the real world. Real materials don't follow exactly this model. No, this is just an analytical form. And again, these things actually come from quantum mechanics, quantum mechanical story of the material, basically. However, there are classical ways of looking at it, or in classical physics, we can also come to this kind of relation from consideration of electron clouds, etc., which is actually very insightful. Because if you don't want to go into the whole quantum mechanical concepts, then it is a very good way of understanding how the material behaves. So in simple terms, this is a simple way of describing the behavior of the permittivity, basically. Now here, as I said, this is a complex quantity, so it has a real part, it has an imaginary part. And this is only for isotropic material. I'm not going into anisotropic material because that's another problem. So here with epsilon, there is another relationship. We can see the refractive index is square root of epsilon. In optics, we do talk a lot about refractive index. This one parameter that is, we describe the material behavior using this refractive index. And there is something called bulk material. So most of the refractive indices that we're talking about is actually the bulk material behavior. You will see in handbooks, there's a lot of measurement actually of the refractive index. But one thing we need to understand is for the simulation purposes, because in many materials, this is the applied scientist point of view. Okay, so in many materials, I mean, many devices, actually thin films are used of different materials. Now, when you are depositing thin films, a lot of, I mean, these values, the refractive index can depend on the deposition conditions and the actual process conditions and actual process types. So the thing is, in most cases, what you would need in the simulation, for the simulation to be accurate, what you need to do is you need to have good measurement of this refractive index. And that's done, a lot of it is done with ellipsometry, but it also has some shortcomings. So, but that is important to be aware that when you do the simulation, you do need to care about actual measured values. So now I will come to a little bit more into this. That is this n or this epsilon. These are actually, they depend on wavelength. As you change the wavelength, even in the visual spectrum, as you change the wavelength, their values can change. This is important to be very aware of this. This is called dispersion, basically. And now, as you see, again, as I told you, that this Lorentz model is good because it shows you how these parameters really behave with wavelength. So what you were seeing in the x-axis is the angular frequency. Now, angular frequency is it's inversely proportional to wavelength of light, basically. And what you are going to see here, you see there is this normal dispersion region. So that means that this is more like, small omega means higher lambda, basically. So meaning you're going to the IR side, and this is more like short wavelength side. So what you are going to see is for the metals, you do see, I mean, even in the visible domain, you see this kind of behavior. Epsilon r means the real part of epsilon, and epsilon I is the imaginary part of epsilon. And so this gives rise to your bulk plasmon behavior, basically the plasmonic resonance behavior. So you see that. And for the dielectrics, you are more or less going to see this behavior. And if you do the square root, etc., you will see that there will be NR and NI. That is the real part of refractive index, imaginary part of refractive index. And the imaginary part of refractive index, as you know, it is associated with the absorption in the material. So it will give you automatically, I mean, for example, when you are doing this photodetector calculations, you will see that the absorption is so important there. You do need to care about absorption. I mean, in any case, in fact, even when you are dealing with these semiconductors, they do have significant absorption in certain wavelength bands. These are things that you need to be aware of when you are doing these simulations. So as I said, that this is a simple model, but it can still show you something. And since I'm here, I would also tell you that when, for these metals, when this situation happens, that is epsilon r is less than 0, that is negative, that causes some amount of trouble in the FDTD algorithm, basically. I mean, if you try to just implement without understanding anything, but I mean, I did that myself and I suffered for some time. And then I realized that this inverse Fourier transform, you have to deal with this inverse Fourier transform. And that's where these analytical models really come into play, and you have to really think about how to use it. Now, let me tell you another more interesting thing that I learned, basically, that is this n, this epsilon, these are described in literature as analytic functions. What are analytic functions? What that means is this epsilon r and epsilon I, the real part and the imaginary parts, are not totally independent. They are actually related quantities. There is something called Cauchy's theorem, and that gives you something called Kramer-Kronig's relationship. So this is a relationship that dictates that NR and NI, the wavelength dependence of NR and NI, are related. Now, I'm an applied scientist. I'm not a pure scientist, so I will tell you that I don't care about equations just for equation's sake. I care about equations when they serve some purpose. The reason I care about the Kramers-Kronig, because you can use it to calculate or estimate the refractive indices in certain cases where you don't really have that estimation. So that's one good thing. So I just wanted to describe these things. So now I will go a little bit into luminescence or light emission, basically. So here you see, if we just consider the photoluminescence for, because to be just simple, etc. So you see, this is a fluorescence or spontaneous emission method. And so in the right-hand side, what you can see is the transitions, the energy transitions that are that guides this fluorescence phenomenon is called singlet transition, basically. So what is happening here is you are from outside, you are supplying some energy. In case of photoluminescence, you are applying some the light, basically UV light. You irradiate it with the UV light. And what you are seeing is that some of that light, then the molecule will go into the higher energy state, and it will come back to the ground state through the radiative and the non-radiative decay, basically. So these two, so then what you are getting here is something called quantum yield of the molecule in free space. So the quantum yield is defined as this is the quantum yield of the radiative decay, and this NR is the non-radiative decay. I mean, quantum yield of the, the decay rate, basically. And so this part, this gamma NR, is actually, it represents the loss through heat. So one of the purposes of this device designs or this fluorescence related device design is to minimize this decay, the dissipative loss, basically, of energy. But so you get this quantum yield. Now this is for photoluminescence that's slightly easier. It is used for characterizing a lot of devices, and particularly the active media that shows spontaneous emission. Now, when you are putting it in cavities, then the radiation yield looks different, and that is called something called Purcell factor. So you do need to calculate that Purcell factor, and that Purcell factor you can calculate using FDTD, which is Maxwell's equations, which is actually classical electromagnetism again. We are not going into the quantum physics here. Notice this, that we are doing the classical physics, and that we can use that to calculate the Purcell factor, basically. So how you do your device design, that influences how this Purcell factor and ultimately the emission efficiency is decided based on that, or the quantum yield of emission. So there is another thing called phosphorescence. That's another process, and it is guided by triplet transition, which is not something I'm talking about here, but it is there. For example, the red emission, especially in case of OLED or organic LED, you do see, phosphorescence, not fluorescence, basically. So that's a more complex process. So here, now, if we are going to talk about LED a little bit more, then what happens is that here, as we already talked about, that we are dealing with spontaneous emission. Those of you who work with lasers, you know that there is another thing is stimulated emission. So this is more incoherent. Spontaneous emission is incoherent in nature. So this is in case of LEDs, because what we are really doing is we are making PN junctions. So what are PN junctions? So you have two semiconductors, one is P doped, one is N doped. And then there is one little thing about it, that the lattice constants have to be matching, okay? then you can grow them into a single crystal, and you can make a p-n junction basically there. And this can be done. You can make the p-n junction with the two semiconductors. While one semiconductor has wide band gap, one can have narrow band gap, and that will give rise to some heterogeneous p-n junction. It doesn't have to be heterogeneous. Even homogeneous p-n junctions can be used under forward bias to see this emission. However, there's a question of efficiency. To maximize the efficiency, there's a lot of device and material engineering that goes into this process. So what is electroluminescence? Compared to the photoluminescence, it's a much more complex method. So what you do is you have the electrical energy, you are applying the electrical energy. So since you have the N donor, P donor, etc., that means you have more, carrier concentration is more than intrinsic semiconductors. And so you are creating this electron hole pair that is called exciton in quantum mechanics, basically. So now these excitons, you are exciting them to a higher state, and then they are coming back to the ground state. This is called recombination process. That is, the hole and the electron is recombining through a radiative decay, and of course there is a non-radiative decay basically. So that radiative decay part, that will give rise to the singlet transition, and then you are going to see the radiation, basically the light that is coming out. So this is the LED device, or it's not just LED photodetectors, etc. All these are, the quantum efficiency needs to be measured. And this is measured in terms of external quantum efficiency, which can be measured actually, the input energy, output energy, and you can measure the EQE, or it's also called wall plug efficiency basically. And then the EQE is actually a product of internal quantum efficiency and the extraction efficiency. This is important to understand because this IQE, or the internal quantum efficiency, cannot be measured. Actually, there's no way directly you can measure. However, you can measure the EQE. And what you can do is the light extraction efficiency. That is something that you can simulate or you can estimate through your models. That's where your classical electromagnetism is coming into work here for you. And so you are using these finite difference models and calculations to come to an estimation of the LEE, basically. And from there, you can have a back calculation of IQE. But that's how it works, basically. So that's why you can use classical electromagnetism to solve this problem. Otherwise, it's a quantum description. There is a quantum description. We should not forget that. So, as I said, that actually, because this simulation that I'm talking about, this is the optical part with classical electromagnetism, how we are trying to deal with this. So this is not just organic, inorganic. There are different types of LEDs. There are big LEDs. There are smaller micro LEDs. So you actually use FDTD for this modeling. However, this is, I need to say, because if you are a material scientist, you will look at it differently. So actually for organic and inorganic materials, the energy bands, the transitions are slightly different. So they are not the same. But still, in our optical simulations, we are not going to look at that part so much. The transitions we are not taking. What we are taking is, as I described, we are more interested in this epsilon, the permittivity of the material. We are going to look at the dispersive permittivities or the refractive indices for each layers, basically. And then you might say, then how are you going to have this light coming out? How you are going to model that? we use radiative dipoles basically. So you can use radiating dipoles in the active medium to emulate that process of emission basically. And this is all done in classical electromagnetism. Now, you need when you do that, so you will understand that these radiating dipoles are how they radiate, that is decided by their polarization direction, okay, their oscillation direction. So then you have all these three polarization directions, and accordingly, the propagation will be decided. You will see, I will show you a little bit, and you will see that some light, while for certain polarizations, light will be coming out, but for some other polarizations, light will be actually guided inside the structure. So that can be seen from this kind of simulations very easily. And you will see that, I mean, in this literature, they will say that in plane polarizations, they can emit out, but the out of plane polarization, that will be more blocked. But you can see from the simulations, you don't have to remember, you can understand that why it is that way. And so because it is incoherent, as I said, that this is more incoherent, so in the far field beam profile, you will need to do an incoherent sum of contributions from different dipoles. And here you are talking about the spatial distribution of dipoles and also the polarization. So what it means is in 3D, it can be really a very intensive calculations. But so another important thing, I mean, the first slide I showed you that there is a challenge in extracting light from high index medium. So that's where these outcoupling structures come in. So you can do some, 1D grating, you can do 2D diffractive structures, you can do some refractive structures, you can do metalenses, you can do microlenses. All sorts of structures are being used and applied to do this. But so what you ultimately need to do is both your LED and the outcoupling structure, and you need to do the simulations on that. And so there are many challenges here, but the point is, so that is also another aspect of LEDs, that is, you do need an outcoupling structure, actually. So here I show you a very simple thing. This is on the left-hand side, what you see is basically a standard OLED pixel, organic LED pixel. So here you have the emission layer, and then you have cathode, you have the transport layer, you have hole injection layer, you have anode, etc. So all these layers, you might think, why all these layers? These layers are there to just boost the quantum efficiency, basically. So because, this is a lot of, device design goes into this to make sure that we have enough IQE, or internal quantum efficiency. So that is what is happening. So now in this case, in this flat multi-layer structure, there are these Green's function methods that can actually solve this. You don't need fdtd. Just if it is just simple this, you can use some Green's function methods. However, there are some if you change the structure a little bit, you want to play with it, then you have to go for numerical solutions. So on the right-hand side, you can see this is just one little radiating dipole that I put here. And you can see that if the polarization is along this, you can see that the light is coming out, basically. And you will see a better, more interesting view of this. That is when you have different, you see this is done in 2D. So you will see the TM mode and the TE mode, and you will see that the moment the polarization is perpendicular, that is out of plane, so you don't have really light coming out in the air so much. It is basically guided inside the structure. While you can only expect the light that will be coming out from these polarization modes. And so, but this understanding actually matters, because in the assumption, when you are modeling, your assumption is that in the active medium, there are all kinds of everything is equally mixed. But in reality, your out of plane mode is not really contributing to the air. So what you can do is you can keep that out of plane mode out of your calculation, and that greatly reduces your simulation time and the amount of the effort that you put into the simulation. So these are little things, but now these are things that comes out from this kind of simulations. Basically, you can understand even without going into the full 3D huge, commercial software. So this is what I was trying to say, that all these computations that I showed here, the things that I showed here, so these are done with both standard and non-standard FDTD and some other methods. But these are all, even the simple calculations you see in 2D, they can be very intuitive, and they can give you the physical insight into a device and how it works, etc. Now here, I did not use any commercial software. These are all developed with my own code, and protocols, some of his, methods, etc. So here, so the point is, I see a lot of people, I actually, in my career, I did hire some interns and people, younger professionals, and they do care about the commercial software and clicking on the commercial software. Yes, that gives you some results, but the issue is it might not always give you the the physical insight into the system. So that's where I think doing some calculations yourself and being able to do things yourself gives you a better understanding of the device. That's all I was trying to say. And thank you for listening.
Okay, thank you, Saswatee, for an enlightening presentation and graphs. As you just commented before going to the audience who were there, you commented that you have not used any proprietary software. So how did you display these beautiful things? Like, have you created the images with with the code and then displayed, or?
It's all, yes, it's all my code actually. What it is, you run, okay, you run FGD with one set of code. I used to do that because, there is, then those results you take and you analyze with another set of codes. So the visualization that you are seeing, some of these are using, MATLAB. Some now I'm trying to use more Python basically, and FDTD itself, a lot of it is run with Fortran, actually Fortran 90 codes, and most of these are 2D. I also did a little bit of 3D calculation, but for that you do need more parallelization and that kind of thing. I understood with time. So if you are really going to do the real device simulations or modeling.
I have a question.
Yes, yes. Please open your camera.
Yes, I have a question about one of your slides. Could you go back to the layers? Yes, over there. I noticed that there are two layers: the electron transport layer, and then this other green there's the star. And then on the right side of the star and on the left side of the star, are those two layers the same or are they different?
I think they're slightly different because what happens is they change the doping levels a little bit, etc. So this is because the carrier transport, basically to make the carrier transport efficient enough, you have to have enough carrier generation, free carriers moving, basically to make sure that sort of recombination efficiency, etc. So for that they do. But if you are interested, I can check out exactly the details.
And the dark blue, that is vacuum, or what is?
No, this is the emission layer.
Substrate?
Which one? This side, this is anode, this is cathode. Yes, there is a substrate or that kind of thing.
All right, thank you. I just wanted to be able to visualize the.
Yeah,
Understand the
it
structure.
can be a better, I mean, I can show you a better structure, but maybe next
Anyway,
time.
I understand.
Okay, Konik will ask a question. Please, Konik,
Yes, please.
unmute your mic and ask the question.
Maybe he cannot use his mic somehow.
Now probably he has come from another device. If it is possible, Konik, can you speak? Unmute your mic.
Okay, I can see your question. Let me read it.
Okay. In the comment.
So his question is about or the use of dipoles for propagation and to incorporate it to polarization. We know that classically the polarization vector in electromagnetic field theory is dipole moment per unit volume, but dipoles can be oriented in different directions. How this affects the modeling? Yes, exactly. That is what that affects the modeling a lot, basically, because it makes it, I mean, what you have to do, because you have is oriented in different directions. So what you are going to say is, yes, it is oriented in different directions, but we are going to divide it into three directions, three orthogonal directions, basically, X, Y, Z, right? So if we can do that, so we have this X component, then Y component, which are in plane, and Z is the out of plane component. And this is where we are going to say that, look, Z component doesn't really give you so much. Maybe there are some measurements that maybe it's a 10% comes from Z component. So keep that. And then you have this XY. So what you have to do is you actually have to do the calculations for each position and for each XY for at each position. So meaning that it is a huge amount of calculation. It becomes a huge amount of calculation. And you have, because it is an incoherent process, so you have to go adding all these contributions at different spatial positions and different polarizations. And then that will give you the result ultimately. It does affect the modeling a lot, actually.
Okay, Konik, thank you very much for writing the question. And if you have any other query, say, Rahul, do you want to put any question?
No, I think Konik has a little comment here that he's saying that in other ways means that 3D modeling is reduced to 1D calculations and add up. It's not quite 1D calculation. You are doing each for each dipole positions, for each polarization, yes. However, you have the structure. Please don't forget the structure. It depends. If you just look at this structure, you don't need to go to 3D. Right, totally fine. However, when you have a complex structure, there are structures where you have to do it in 3D. However, you can exploit the structural symmetry, like you have a circular symmetry. Then you can use the circular symmetry and reduce the problem. Yes, you can do that.
Okay, Konik, hope for the time being he is satisfied with this. And Rahul, please, if you have any question, you can talk or you can.
Thank you too for your good questions and interest.
Yes. Konik is always intuitive and I mean, it is good. He was in a symposium in Ahmedabad. He returned yesterday, and that is good. Otherwise, we would not have got him in the questions. Okay, and just because even you are two only attendees are there, we have written some poll questions. So I will start polling. So you two, please vote these questions. The first one is, did you find the mini workshop on computational photonics useful? And
I hope that some other people who registered would join. Anyway, so you please vote Rahul and Konik, and another question is there in the poll. Okay, I'll publish the result. Okay, it is there. Okay, and there is another poll. Let me see why it is not showing. Yes. Another question is, which topic would you like to see in the next session? There are 4 options. Anything you can choose. Industrial application is being shown. So I'll also publish this. Back to the list. So the last question is, we are planning to host an on-site workshop on computational photonics. So would you join an on-site workshop on computational photonics in Kolkata on January 9, 2026? Okay. Not voting. Okay. Anyway, there are not enough people here, but we'll be trying to host the on-site workshop with Professor James Cole and Dr. Saswatee Banerjee in Kolkata on January 9. So hopefully by next week, some other people will join. And this is the second episode, and the third episode will be part 3, and that will contain what? Please, Saswatee, can you that on 20th December, what will be the content of your?
Yeah, I actually forgot what I wrote.
Okay, okay. I'll just see in the post. It is there. Okay. The part 3 is real-time propagation of light in complex media, which will be streamed on December 20. Sorry, the date 2025 and Saturday, same time, and hopefully with the same system. Although we are using now 2 systems, like we are using Zoho webinar, and also it is live streamed via Restream simultaneously to LinkedIn and YouTube. And we could see the comments on LinkedIn, and we could even reply from Restream also to YouTube, but LinkedIn is not connected. My comments, replies are not going to LinkedIn. Anyway, thank you, Konik and Rahul, to be here inside the webinar system and putting some question and making it a real webinar. That way, exchange between the speakers and the audience. And hopefully on 20th December, it will be with more people, the research scholars community, and even say some other students. So any last remark, Professor Cole and Saswatee, please say.
Yes, I think this format was pretty good. One talk on the methodologies, and then another on the applications. So I think the next session can, I think, follow a similar format. That I would talk about the theme is complex media, and a complex one aspect of a complex medium is nonlinearity. So I will discuss how one can solve problems for light propagation in nonlinear media.
Okay, it looks like on YouTube there are other participants according to Konik. And Rahul, thank you definitely for coming, joining, and listening. And yeah, please interact more. It's very, nice. It's very pleasant to be able to really interact and talk to you.
I would also say that the questions were very good. They were very, I think it shows that the people who ask these questions have a very high level of knowledge
And
I'm
interest.
glad that, and interest as well.
So we will end this stream, and before we end it, we'll remind that the coming Saturday, December 20, 2025, we'll stream the part 3 of this. And in January in Kolkata, it will be in the Department of Applied Optics and Photonics, University of Calcutta, as they have agreed to host the on-site workshop on computational photonics. So with that, we are ending the stream on this stream and other places. And what is that in stream? From here it will go. Okay. Okay. We'll end it here. We'll end it here.